Okay, so we are going to review nuclear chemistry in chapter 21, and I'm going to go through this fairly quickly because honestly, a lot of it, until you get toward the end, is just a review of Regents Chem. Jot down any notes on your note packets that things that you may have forgotten or that you want to recall later. Just a quick review of the atom. You know that we have the nucleus, and in the nucleus are our nucleons. They refer to the protons and neutrons. The protons is also our atomic number, and the number of protons and neutrons together is our mass number. Now we know that not all atoms of the same element may have the same mass, and that's because they differ in a number of neutrons. So we refer to these as isotopes. Isotopes are of the same element. Their atomic number is the same, but their mass numbers differ due to their differing number of neutrons. 3 examples here are the different isotopes of uranium: 234, 35, and 38. 235 is often used in fission reactions, and 238 is often used in geological dating, or the dating of rocks. So some nuclei are stable and some are unstable. A lot of it has to do with the neutron to proton ratio. The closer that the neutron to proton ratio is 1:1, the more stable the atom is. If an atom is unstable, that means that they are radioactive, and we refer to these as radionuclides, and they can automatically or spontaneously, as we refer to it, decay, releasing a nuclear particle and turn into a new element. Let's look at some of the ways in which this happens. You know that when we look at a chemical equation, that the atoms or number of atoms on both sides of the equation need to be balanced. In nuclear equations, the atomic number and mass number need to balance. So we balance the atomic number and we balance the mass number. When you release a nuclear particle, the atomic number or the mass number may change depending on the nuclear particle that is released. So let's review alpha, beta, and gamma radiation. An alpha particle has a mass of 4 and it has a charge of 2. It has a relative penetrating power of 1. So you can see, compared to beta and gamma, that alpha particles are the weakest type of radiation. You don't have to know its mass in grams, but it is listed there. It might be used in making some calculations on some sample problems, but I wouldn't expect you to memorize it. Then we have the beta particle. The beta particle is also known as an electron. It has a mass of basically 0 and a charge of -1. And it has a penetration power of about 100. And then we have the gamma particles, which have no mass, no charge. These are the equivalent of high energy photons, packets of energy, equivalent to X-rays, and the relative penetrating power is 10,000, so very, very strong. You can remember these weakest to strongest because they also go in alphabetical order: alpha, beta, gamma. We're going to review 5 types of radioactive decay: alpha decay, beta decay, gamma emission, positron emission. Now remember, a positron is simply a positive electron, mass is 0, charge of +1, and electron capture, which is different from beta decay. They both involve an electron, but electron capture, it means that the nucleus or the atom is taking in an electron. Beta decay, an electron is being released in the decay process. So here we're looking at 4 out of the 5 types. I want to preface this by stating that we are not looking at gamma radiation because gamma has no mass or no charge. So your starting element and your ending element would remain the same except for the releasing of energy. So we're going to look at the other 4. Notice that your nuclear equation is written in generic terms, okay? So A being the atomic number, Z referring to the A referring to the atomic mass, Z referring to the atomic number. So with alpha emission, you can see that the atomic number of the new element Y decreases by 4, so atomic mass minus 4, and the atomic number decreases by 2. And then you release an alpha particle. With beta emission, you can see that the atomic mass stays the same because the mass of an electron is virtually 0, while the atomic number increases by 1. Because if I have an atomic number and I add a -1 to that, remember that has to equal the starting atomic number on AZX. For positron emission, very similar to beta emission, our atomic mass is remaining the same, but our atomic number is going to decrease by 1, so that the charge before and after the reaction remains the same. And in electron capture, you can see that a electron is being taken in by the nucleus of the atom. The new element has the same atomic mass, but the atomic number has decreased by 1. Here's an example of alpha decay. So you're losing an alpha particle that has a mass of 4 and a charge of 2. Remember, an alpha particle is the equivalent of a helium nucleus. So here we're starting with uranium-238. And when I release that alpha particle, the new element that forms is thorium-234. 234 and 4 equals 238, 90 and 2 equals 92. Remember to treat the arrow as an equal sign, and you can't go wrong. With beta decay, we're losing a high-speed electron from the nucleus. It can be written as 0, -1e, or with the beta symbol. Here we're starting with iodine-131, which is used for thyroid testing in medical diagnosis because it has a very short half-life. We're releasing the beta particle from the nucleus, and the new element that's formed is xeon-131. Notice the mass number didn't change. The atomic number increased by 1 because a 54 and a -1 equals 53. Gamma emission, as I noted earlier, is the release of high energy radiation, and it almost usually accompanies the loss of another nuclear particle, but by itself, mass and charge would not change. Remember, a positron has the same mass but opposite charge of that of an electron. So here in positron emission, we have a 0 + 1 positron particle being emitted. What that means is that our atomic mass number stays the same, but our atomic number will decrease by 1 to accommodate for that positive charge so that both sides of the equation have a 6. As you see here with electron capture, an electron is captured from the surrounding electron cloud and taken into the nucleus of rubidium, forming krypton 81. The mass number didn't change, but the atomic number decreased by 1, so that you have a 37 on both sides. So what are the sources of these nuclear particles, or where are they coming from as they relate to the atom? Well, beta particles are probably the easiest to understand because they're electrons, and they're simply coming from the electron cloud of the original element. Positrons can form from the conversion of a proton into a neutron. And when that happens, a positron is also released. And it can be written two ways there. With electron capture, what's happening is when an electron is taken in by the nucleus, it unites with a proton and forms a neutron. So this chart just reviews some of the nuclear particles that are found in reactions, and we've gone over all of them. I didn't specifically talk about protons because we already know what a proton is. It's just simply a hydrogen nuclei. So I mentioned this earlier in the lecture, nuclear stability. How do we determine whether something's going to be radioactive or not? It has to do with the neutron to proton ratio. Any atom with more than one proton will have repulsions between the protons in the nucleus. Why? Like charges repel. There is a strong nuclear force that helps keep the nucleus together, and it's the neutrons' role in that strong nuclear force, because it stabilizes the nucleus. It balances the protons. It helps balance the protons, even though they are neutral. It is the ratio of these neutron to protons that help determine the stability, or the degree of stability. For small nuclei with an atomic number less than or equal to 20, their neutron to proton ratio is pretty much 1 to 1. So if you were to take carbon with a mass of 12 and subtract the protons, right, you have 6. 6 divided by 6 is 1. So your neutron to proton ratio is 1 to 1. As the nuclei get larger, though, it takes a larger number of neutrons to stabilize the nucleus. So from this graph, you can see that the shaded region is what we call the belt of stability. And it shows which nuclides would actually be stable. There's different regions that you have to understand. So number 1 is the region above the belt, right, where your dominant decay mode is going to be beta emission. So those are not stable above the belt. Then you have 2, the nuclei below the belt, where their dominant decay mode will be either positron emission or electron capture. And then nuclei that have an atomic number greater than 84 will have the dominant decay mode of alpha. So you can see the red line is your 1 to 1 neutron to proton ratio. And then you can see, as you veer from that line, how your stability changes and what the dominant particle will be. So to understand why this happens, if you look at the nuclei that are above the belt of stability, you can see that they have too many neutrons because their neutron to proton ratio is 1.40. So they need to get rid of neutrons. They have too many neutrons. So the way that they do that is by emitting beta particles. The nuclei below wind up having too many protons. So you can see that the neutron to proton ratio is 1.15. How do they do that? They are going to get rid of either a positron or capture an electron. Both will have the same net result because they have no mass. However, electron capture, you're taking in the -1, positron emission, you're releasing the +1. So both will have the same effect on the atomic number. And then, as I said earlier, anything that has an atomic number greater than or equal to 84 is going to decay by alpha emission. Now, some nuclei have such a large difference in their neutron to proton ratio that they can't just stabilize by undergoing one nuclear transformation. So they can't just release one particle and become stable. And an example of this is uranium. So you can see from this diagram, okay, that uranium undergoes alpha decay, and it turns into thorium-234. And then what happens is it undergoes beta decay several times, okay, turning into a more stable form of uranium. And then if you follow all the arrows, each arrow represents a decay mode. You can see then that uranium-234 then undergoes alpha emission 1, 2, 3, 4, 5 times to get down into a form of lead, which then undergoes several beta emissions, another alpha emission, several more beta emissions, and then an alpha emission, which finally gets it to 206, lead-206, 82. That is a stable form of lead. So if you add all these up, it went through a multitude of decays until it finally got to a stable form. And all of these are happening spontaneously. This isn't something that you have to memorize. It's just an observation that scientists made. They refer to them as magic numbers of 2, 8, 20, 28, 50, or 82 protons, or 2, 8, 20, 28, 50, 82, or 126 neutrons will result in more stable nuclides. Nuclei with an even number of protons and neutrons tend to be more stable than those with odd numbers. So this is just one of those interesting factoids, if you will. And to break all that information down even further, you can see here that when your protons and neutrons are an even number, you have the most stable isotopes. When you have an odd number of protons and neutrons, you have very, very few stable isotopes. So nuclear transmutations can happen several ways. We've just been talking so far all about spontaneous or natural transmutations, starting with radioisotopes that are unstable and decay all on their own and then until they become stable. However, we can induce nuclear transmutation by causing a nuclear particle to collide with the nucleus. We can do this by using a particle accelerator, often called an atom smasher. They're very, very huge, they're very, very expensive, and they involve using strong magnetic and electric fields to make the particles move so fast that when they slam into one another, it causes the atom to change into something else. And then we have what's called a linear accelerator, which basically uses different tubes of variable lengths depending on how fast you want to accelerate the particle, and it shoots it down the tube and into the nucleus. Then there's another device called a cyclotron that uses D-shaped magnets to keep particles moving in a spiral, and then they hit the nucleus. And then you have something called a synchrotron, which accelerates particles in a path that is circular as opposed to spiral. So on the left here you have an example of a linear accelerator, and it's showing you the path of the particle, and you can see that it also has an alternating voltage source, and then you have the target, and below it you can actually see what it looks like above ground. So that big white line is the entire particle accelerator. And on the right here you have an example of I believe this is a cyclotron, and you can see it also above ground. So pretty massive, and as I said, very expensive. Other types of nuclear transmutations include the use of neutrons. These are mostly used in medicine, and they're prepared by bombarding neutrons at a particle which won't repel the neutral particle. Interesting enough, your transuranium elements, which are those elements on the periodic table located after uranium, were actually discovered by bombarding isotopes with neutrons. And what they found out was it caused them to turn into a new element. So they are synthetically made. And then even larger elements, atomic numbers higher than 110, were made by colliding large atoms with nuclei of lighter elements with high energy, and also synthetically created subsequent elements from them by doing that. So how do we write nuclear equations? Well, here's one way. First, you started with nitrogen. You bombarded it with an alpha particle, and you turned it into oxygen 17, and you also released a proton. Or you can use the symbols. So you have a choice. You always write the starting element and the ending element, and then you can either use the symbol of the particle or you can write the particle out. I tend to write the particle out so that this way I can make sure that my mass and atomic number all balance on both sides of the equation, but it's really what you feel comfortable with. And then the least favorite way is what you see before, is you have the target nucleus followed in parentheses by the bombarding particle, followed by the ejected particle, and then the product nucleus. This is the least, I guess, preferred way. It's written in textbooks sometimes that way, or in research documents or literature, but usually not practical for class. As you already learned in kinetics when we talked about rate laws, radioactive decay is a first-order process. Remember that radioactive decay is the amount of time that it takes for 1/2 of the sample to decay. And you're already familiar with the formula K equals 0.693 over T to the 1/2. Well, actually it's written as T to the 1/2 equals 0.693 over K, but here you're solving for the rate constant. This is just a list of examples of natural isotopes, their half-life, and their decay mode, followed by synthetic isotopes that were produced by possibly bombarding natural isotopes and turning them into something else, their half-life and their decay mode. Notice iodine 131 has a half-life of 0.022 years. It's very small. I think when you convert that into days, it's a little over 8 days. Remember, we do not want something that we put into the body to have a very long half-life. We want it to be eliminated as soon as possible so it doesn't damage any of our other organs or cells. Okay, I'm going to stop this lesson here, and then I will continue with the second half on the new video. If time permits, please start the second lesson.